Welcome to the 2016 Gilfillan Memorial Award Lecture. We are really in for a treat as we hear about the fascinating field of transparent electronics, the materials that are transforming our lives and driving the economy. Electronic materials play an increasingly important role in the generation and storage of energy and fuel the development of next generation electronics. I'm sure many of you have smart devices with you. Tonight, we can learn more about the materials and the science inside all of those devices. But before we enter into the world of transparent conductors and superconductors, I want to thank the Gilfillan family who is here for their generous gift that enriches our campus community, Corvallis, and the region. This gift enhances our efforts to share scientific discoveries and cutting-edge research with other students, faculty, staff, alumni, and friends. Thank you so much for your strong support for science, which has been a long-standing tradition in our college. So I want to recognize the Gilfillan family members and their guests who are here today. We have Frank and Ellen Gilfillan Johnson, right there. And their guest, Julita Fong, and her sister here. Bob and Nan Jensen. And a niece, Kay. I think we also have Tammy and Lionel Wood and their daughter, Ashley, here. Thank you all again for coming and joining in this wonderful event. They and other family members who could not be here established the Gilfillan Memorial Award to honor Francois A. Doc Gilfillan, who served as the Dean of the College of Science from 1938 to 1962, and as the acting president of OSU from 1941 to 1942. This gift honors Doc Gilfillan's life and recognizes his extensive service and the contributions to OSU and our college and the field of pharmaceutical chemistry. He was truly an inspiration to colleagues and the students alike. So this Gilfillan Memorial Award recognizes distinguished scholarship in science by honoring faculty with extensive scholarship and scientific accomplishments and who are widely recognized by their peers. So tonight, I'm really honored to introduce to you the 2015 recipient of the F.A. Gilfillan Award for Distinguished Scholarship in Science. She is globally renowned for materials physicist, as well as an outstanding researcher, a teacher, a mentor, and a tireless champion of physics education. She's also an extraordinary scholar, teacher, colleague, and most importantly, an outstanding citizen. You know, I'm talking about Janet Tate. Since 1984, 31 faculty in the College of Science have received the Gilfillan Award. But this year, this is the first time, this is the first ever, the Gilfillan Lecture is presented by a physicist. Remarkable. It must be that the Mercury and the Sun are aligned at the perfect time. Janet joined our faculty as an assistant professor in 1989. Originally from South Africa, Janet holds a PhD from Stanford University. In a career spanning 25 years, Janet has skillfully balanced brilliant research, creative, cutting-edge collaborations, outstanding teaching, and mentorship. She collaborates with other material scientists in the Center for Sustainable Materials and Chemistry and across Oregon State. Her research is focused on creating new semiconductors with transparent circuits that will have electrical and optical properties to help solve some of the world's pressing problems, like efficient conversion of solar energy and efficient light emission. So Janet's work involves undergraduate and graduate students and has led to a new class of materials. Like many in Oregon, she is very humble, and she is always quick to recognize the contributions of her students and her colleagues. She sees the role of scientists as not only producing discoveries, but also producing the people who will make future discoveries. A global leader, Janet has garnered many OSU, national, and international accomplishments and honors. It's impossible to mention them all here, but I can highlight a few of them to show you just what an extraordinary scholar, teacher, colleague, and person Janet is. Just to name a few, last year, she was named the first Dr. Russ and Dolores Gorman Faculty Scholar in the Department of Physics. The Endowed Award recognizes faculty who bring distinction to the College of Science, connect with industry, and have a strong record of innovative research with practical impact. Last fall, Janet was elected a Fellow of the American Physical Society, which is conferred upon no more than half a percent of the Society's membership. This is really a testament to her outstanding contributions to physics and the recognition of her research by her peers, both nationally and internationally. In total, 12 of our faculty have been elected APS Fellows, which also shows the strength of faculty in science. Janet was one of the 7 international scientists who received the Technical University of Munich Ambassador Award in 2014. She received the OSU Alumni Association Distinguished Professor Award last year. Janet has been a leader at OSU as well as across the nation in developing Paradigms in Physics, an NSF-funded program that has been in the Department of Physics for more than 17 years. It is regarded as a standard in physics education nationwide. This innovative curriculum approach teaches students to think like physicists. She currently chairs the American Physical Society's Committee on Careers and Professional Development, which steers the national effort to link physics research with industry. Janet has received numerous awards for her excellence in teaching and research. Janet also actively encourages diversity in science and led efforts to host a national conference for undergraduate women in physics in January. That may not sound so extraordinary, but women in physics are a rare breed. They are very rare. Women in the fields of physics and material science are even more rare. So Janet is something of an anomaly. In fact, NSF survey regularly reports that among STEM fields, the proportion of women is lowest in physics, engineering, and computer science. The American Institute of Physics reported that women made up of just 13% of professional rank faculty members in all physics degree granting departments in 2013. I'm very proud to say that OSU's physics department has 6 women, which is close to almost 30% of its faculty, considered quite high by national standards. So when I talk about excellence, diversity, and harmony in our college, Janet and our physics department are as shining examples of our One Science community. So I hope Janet's presentations tonight might inspire some of future scientists, especially women, in the audience. So global data reveals that the representation of women is lowest in physics, followed by materials science at 15% or less. So both of these fields have such an important impact on all our lives. So it's an exciting time to be in science, and as you may know, science is better at Oregon State. Without further delay, let's hear about our materials world and learn to think like physicists as we explore the science behind it all. Thank you so much for joining us in this celebration of science. Please join me in welcoming Janet Tate.
And you were expecting Madonna. Thank you so much for that introduction, Sastry. Thank you all very, very much for being here. I'm honored to see so many people here. And thank you in particular to the Gilfillan family for coming tonight and for your support of science at Oregon State. We're truly grateful for that. Doc Gilfillan was a visionary person and a very accomplished man. And it is a great honor for me to accept the award that is bestowed in his name, and to join so many of my fellow faculty members in the College of Science whose work I admire so greatly. I went over to the library the other day to find what Doc Gilfillan had written, and I found two things that I wanted to share with you. One of them was that he understood that research is a curiosity-based thing. You can go looking for something and never find it, but you probably will find something else while you're looking for it. So you should keep looking. He said if it's scientifically interesting, we'll find a use for it eventually. The other thing that he was about was education, and that's something that resonates with me greatly. He said educate for tomorrow, and that's of course what we have to do. And he was one of the co-founders of OMSI, the Oregon Museum of Science and Industry, and his emphasis on being able to do science is something that I've taken to heart and I really strongly believe in. I'm going to talk about a materials world, so let me tell you about my world first. You can see from this map that I stole from Google here that I've lived in a number of places around the world. It's not necessarily a typical career for a scientist to have lived in all of these places, but anybody who's a scientist knows that science is an international endeavor. You always end up meeting and working with people in other countries as well. And this is something that I really am grateful for, that my career has spanned so many places. So I started out in the southern tip of Africa over here at the University of Natal, now known as the University of KwaZulu-Natal, this building here. And this picture over here of my graduation is to remind me that I was 21 once upon a time. Next to me is my sister Alison, who's in the audience tonight. She came all the way from South Africa. She has everybody beat as far as distance is concerned. But she also represents my family, and they were a very important part of my career too. We are non-scientists in my family, except for me, bankers and nurses and lawyers and teachers and farmers, but they're all about education and supporting people in what it is that they want to do. And for that, I'm very grateful, and I wish that for everybody. But coming from a family of non-scientists, they didn't necessarily know how to mentor me in a career in science, and that fell first to this man, Owen de Lange, who was an undergraduate professor of mine, and he said to me back in 1981, when South Africa was politically very isolated and geographically quite far from, there was no Skype, you couldn't just jump on a plane that easily. He said, you should go to America. So I said, oh, okay. And I went off and found some fellowships and scholarships, and I got one, and I took him a list of places that I had been accepted to, and I said, what do you think about these places? And he looked down the list and he said, you should go to Stanford. I said, where's that? So I went to the library and I discovered that I'd been offered a wonderful opportunity, so I listened to him, which you should listen to people who know more than you do. And I went across the ocean to Stanford. Also a very beautiful place, and I spent 5 years there getting my PhD in physics, and I studied superconductivity. That was my first introduction to that topic. And I had the pleasure to work with my advisor there, Blas Cabrera, a wonderful scientist, amazingly intuitive, did these beautiful, gorgeous experiments, and I learned an enormous amount from him about physics and also how to be a physicist. He was a wonderful mentor as well, and he encouraged me to go to the next phase of my career, which was across the sea again. I had a little visa problem that I had to take care of, so I went to Germany, to the Technical University of Munich, where I worked under the direction of Professor Helmut Kinder, who himself is a very, very accomplished scientist. And I learned about high-temperature superconductivity, which had just hit the airwaves at that time when I went there. It was a new field, and that's when I first started learning about materials physics of the kind that I still practice now, looking for new things, trying them out, making thin films, and so on. But I also learned a new language. Doc Gilfillan would be very happy about that. I think he spoke 9 or something. And a new culture, and made many connections with scientists in Germany that I maintain today, both professionally and personally. It was a wonderful time. But then I wanted to pursue a career in teaching and research, and a university seemed like a good place to do that. And so I started thinking about faculty positions. But in addition to a degree at Stanford, I had acquired a husband who also was a physicist and also wanted to be a teacher and a researcher. And that meant that we had what physicists call a two-body problem. But fortunately, that was solved by OSU. And David and I joined the physics faculty in 1989, and we raised our family in Corvallis, and we've had a wonderful career at OSU. There have been so many people at OSU who have been wonderful influences in my career. They have been mentors, and I can't possibly mention all of them here, but thank you all of you. You know who you are. But since we're talking about material science, and I do want to mention 2 people in particular, my colleagues Doug Kessler from chemistry and John Wager from electrical engineering. They've been collaborators in this materials endeavor for the last 20 years, and it's this connection of people, 3 people who were trained so differently, bringing their talents to bear on one problem that's made science interesting and fun, and has been a wonderful collaboration. Thank you both. What can I say? These are the people who do all the work. These are the students and postdocs that I've had the privilege and the honor to work with over the last 20 years, and they have done wonderful things. I'm really proud of them and very grateful to all of them. Undergrads have been a big part of my lab as well, and I think it's really important that undergraduates should be in a physics lab to figure out how things work, how much fun science can be, and how much fun science isn't sometimes. And all of these people have done research in my lab at some point or another. Most of them have written theses, and they have gone on to wonderful careers, all of them. And these are some of the places that the students have ended up, and the companies that have them are lucky to have them. And you can see that Oregon and the world have benefited from these people too. So they're my lasting legacy, I think. So I'm going to now talk about the scientific part of my talk. I'm going to divide it into 2 bits, talk about transparent conductors, which are really transparent semiconductors, and superconductors, which is the part of my career that I started out at. And this is the kind of the latter part of my career. And mostly what I do is to think about materials, worry about how electrons move around in materials so that you can get charge from one place to another. It seems kind of mundane, but that's really a very important thing about conductors. You have to get electrons from one place to another to make them do the things that you want. So let me begin with thinking about conductors, metals. If you want to get electricity from one place to another, what you do is you get hold of a metal. Gold, silver, copper. Now metals are things that transport electrons rather well from one end to another. They conduct quite well. And the reason they do that is that there are lots of electrons in a metal, and they are not very well tied to their host atoms, sort of like teenagers, you know, they're all far apart. And they move around in clumps too, like this. And the reason they move so easily is the reason that they're good conductors. But that also means that when light shines on a metal, these electrons can move very easily to follow the electric field of the light, and they actually just reflect the light back out. So that means you see light coming back at you, and the light doesn't go through. So metal is not a very transparent thing. You might have noticed this. They conduct well, but they're not transparent. If you want something transparent, you'd opt for glass anytime. It's very good. You can see through it. But glass is not conductive. You've probably noticed that too. And that's because the electrons in glass are not free to move like this. They're kind of like babies. They cling to the parents. You know? And these electrons are bound up in the bonds. They're not free to move, and so they're transparent, but they don't conduct very well. So wouldn't it be nice if we could combine these two properties, transparency and conductivity, together? You'd get a transparent conductor. How many of you own one? More hands, please. All right. Yeah, you all own one. Okay. Every day in the US, we produce acres and acres of transparent conductors, and we put them on these touch screens here, and they allow us to communicate with these ever-present devices. Probably some of you are surfing the net right now with them like this. And we need them because those electrons that move around easily, we want to be able to scroll like this and tell the machine what we want to do. So our fingers actually interact with the electrons a little bit because we're a little bit conductive too. The other place you might find a transparent conductor is on the front end of a solar cell. So a solar cell is a thing that takes light and it separates charge. That's great. But you have to get the charge out of the solar cell and into the battery, into the wires to do the work you want to do it. So you need a metal. Oh, but you need to get the light in too, don't you? So you need a transparent metal. So we use indium tin oxide. That's the most commonly used one for that too. And the last place you might have encountered a transparent conductor is on your windows. If you have highly efficient windows here, the reason that a transparent conductor works the way it does is that it doesn't have quite as many electrons as a metal, but they still move around quite easily, with the result that they do reflect some of them, but really only the infrared ones, the low energy ones that cause things to become hot, the infrared light. So when it's hot outside and the infrared photons come from here, a transparent metal or transparent conductor will reflect them, keeping the room inside cool. But in wintertime, when you bring the heat inside and you heat up the house and you've got a fire burning in here and it's hot in here, you want those infrared photons to stay inside. And so you need a metal that's shiny in the infrared, and that's what a transparent conductor does. Now, that's all very nice, but it's old news. We've had these around for a long time, long before I got into the game. And what John and Doug and I did when we wanted to study transparent conductors was not to make a better transparent conductor, because although there are some things that you would like to solve here, some problems you want to solve, it wasn't this property that we were after. We didn't really want to make a better transparent conductor. What we wanted to do rather was to make a transparent semiconductor. Now, silicon is an example of a semiconductor. Semiconductor is somewhere between a metal and an insulator. That's why it's called a semiconductor. Right? So, and the silicon is what you find inside all of these little gizmos, these computers, this thing over here, that is the brains and the logic that pushes the ones and zeros around and makes our lives so nice. Right? So that's silicon. And the thought is, well, if we could make those kinds of properties that silicon has and make them in a transparent material, well, then we might have transparent electronics. So the thing about a superconductor, I beg your pardon, a semiconductor, is that it has, it's conductive like a metal, but you can control the conductivity. You don't have that many conductors. You have just a few, and you can make it as few as you like and up to almost as many as you like. And there are also two types of conductivity. We call them, very originally, negative type and positive type. And it's the combination of this negative and positive type that makes the semiconductor silicon, being able to control it like that, into this bright, wonderful thing that makes computers and makes logic work. So if we could do that in a transparent material, maybe we could make these transparent electronics. And we can control the transparency in a semiconductor too, as I'll show you in a minute. Now, what could we do with transparent electronics, as opposed to just a conductor, which is a metal that you can see through? What could we do with transparent electronics? Well, Hollywood can tell you. There's Tom Cruise doing something brave and daring with screens and stuff, and Robert Downey Jr. doing something else over there. But Hollywood cheats. They just make up the stuff, right? They just put it there, and they made transparent electronics. But Samsung actually does make them. And so here, for example, is a weather app which is on the glass, and here's this person trying to figure out what the weather is like outside, just in case you can't see. But it can tell you about tomorrow and the next day as well. And they keep making them better and better, and they have now have these screens which are mirrored, and you can swipe over here, and the shutters come down and so on. So they just continue to make them better and better. So they really are around. You can also find them. We carry our glass around with us. We have windshields, and so heads-up displays are an example where you might want to know that there is an obstacle here that you should be careful and not hit this person, or there is, you could navigate and so on. So heads-up displays have been used in the aviation industry for some time, but now it's coming to the point where they're in cars as well. And you can keep your eyes on the road and have the electronics that you need right there. And transparent electronics is one way to do that. You could have this in the windshield of your car. Or you could just make better electronics. And while this is my colleague, John Wager. And John, this is the only time you're going to be on the same screen as Tom Cruise and Robert Downey Jr. While John was waiting around for me to make P-type semiconductors, he went ahead and made some transistors out of N-type materials as well, and succeeded in making some transistors that were just, well, they were transparent, but they were just better than the other ones that people had used up until that time. And so here they are sitting behind the Retina display in the Apple display here. And the fact that they're transparent actually doesn't matter very much at all. And so that's another example of finding something when you weren't exactly looking for it. So let's talk about the science now. I'm a scientist. I always like to know how things work, so indulge me a little bit while I assume that you also want to know how things work. It won't take too long, and the pain won't be too bad, I promise. So what does transparent mean? You're looking at the walls right now. You can see through the air, right? So let's take a look and see what it means to be transparent. So you are here, and you're looking at the sun, and what do you see? Well, you see all the colors of the spectrum, don't you? Almost all the colors of the spectrum. There are just a few little places here where the color has been stolen away, but mostly when you look through a gas, you see that it's clear, and you say it's transparent. Now, why is that? Well, we can understand hydrogen. We're physicists. One electron, one proton. We can tell you anything you want to know about hydrogen. Anything else, but hydrogen, we've got it down. And what quantum mechanics tells us is that electrons in hydrogen live in very particular states. They're allowed to have this much energy and that much and that much and no more and no less. And in these places, they can't be at all. It's like being in these seats, right? You can sit in the row, you can sit there, but you can't sit in between the seats. Okay, so along comes a photon, a ray of light, and this one is red, and it comes along to the electron, and if it has exactly the right amount of energy, then the electron can go to one of these other states if the energy is exactly correct. And then the photon is absorbed. But if it doesn't have the right amount of energy, then it can't make the electron jump to another one, and it comes through, and we see it. And that's why hydrogen is transparent. So we've understood. Now, what does hydrogen have to do with indium oxide or any of the transparent things that I've talked about? Well, what we do is to take the model that we had for hydrogen and say that the solid that we have, they're not just specific energy levels like this, but the places where electron can live is in a box of energy. So this diagram here, these boxes represent places that the electron is allowed to live. Those energies are okay. And the places in between are not allowed. Electrons are not allowed to be in that. Those are the rules of quantum mechanics. Electrons obey them, you obey them, everybody obeys them. We don't even need police, right? Do that. So let's get rid of the hydrogen atom. We don't need that anymore. Now the solid has lots and lots and lots of electrons, not just one. So we'll represent them here. We'll fill up these boxes. These are all filled up electron boxes. But we've got too many boxes. It's too complicated. So let's just throw away a couple of boxes, right? So we've got these boxes here where the electrons are allowed, and then one box over here where the electron could be, but it isn't right now, and a space in between, which we call the band gap, where the electron's not allowed to be. So now we do the same story all over again. We take all the colors of the spectrum, from red all the way to blue, the ones you can see, to purple. And they have different energies. The red ones are the low energy ones. The blue ones are the high energy ones. And along comes the red photon, the red light ray. And this electron doesn't have anywhere to go if it absorbs that one. So the red one just goes right through. How about the blue one? It also doesn't have anywhere to go. There's nowhere that an electron could absorb a blue light photon and end up in a place that it's allowed to end up. So the blue one goes through too. And in fact, all the visible colors go right through, so that's what makes it transparent. And so here is a picture of a transparent material. Now, if we make the band gap smaller, make this box bigger and the allowed area a little bit smaller, then the red light still goes through, same reason as before. But this time, the blue light can absorb, the electron can absorb the blue light, and it'll end up over here. And that means that all colors with energies bigger than this band gap are absorbed. And so this material transmits all the red and all the green, and it looks yellow. Okay. And this one looks red. So now we know why things are transparent. But conductivity, the ability to move the electrons around, well, that's a little bit more difficult. So let's think about this a minute. Let's do an experiment for the moment. Imagine that you were to put, you don't have to do the experiment, but you could think about doing it. You could put your arms out like this. Whoops. Really, these gizmos. If they were transparent, it would work. Okay. See if that works. Yeah, anyway. Okay, so if you were to put your arms out like this and touch the person next to you, then there would be two arms between each of the two people, right? And that is a chemical bond that is satisfied. Chemical bonds like having two electrons in them. Electrons don't want to go anywhere. And so those electrons then stay in the bond and they don't move. So that thing is called an insulator. And that's represented in my picture here by this filled box over here. These electrons don't have anywhere to go. There's no space for them to go. So this thing is an insulator. Oh, but there's lots of space in this one up here. But there aren't any electrons. So there's nothing to go anywhere. So this thing doesn't conduct at all, and it's an insulator. So how do we make a conductor out of something that we learned how to make transparent? Well, let's think back to our experiment again. And if you imagine your arms out like this, and I'm going to now replace one of you with a person with 3 arms. Okay, so 2 of them get used in the bond, but then there's 1 extra arm, and where does it go? Well, in my picture here, that extra electron now, let's not talk about arms anymore, what we do is in real life we find if we take silicon, for example, we find in an element, in this case phosphorus, that has 1 extra electron. Silicon has 4, phosphorus has 5. It uses 4 of them to fill up the bonds, and 1 more that goes and lives over here. Now I have a means to control the conductivity. I can put in as many phosphorus atoms as I want. Well, the people at Intel do that, right? They know how to do all of this stuff. And they can put in as many as they want or as few as they want to get the conductivity that they want out of it. So really what it amounts to is finding the right band gap and putting in just enough electrons, just enough to do the job that you want. Now these electrons over here will conduct just like the electrons in the metal did, but there are not as many of them, and we have control over it now. And this is the kind that we call the negative conductors, or the N-type. But there's another way to do this. Now if you do our experiment again, and we put arms like this, and now I put a person with 1 arm in there or none, then there are some bonds that are not satisfied. And I represent that in my picture like this. And so if there are just 1 arm between you and the other person, then another arm could come over here from somewhere else. Let's forget the arms and just do electrons, right? These analogies only go so far. My students will tell you that too. No, forget the analogies. All right, so now we have bonds that are missing one electron, and the electrons can come from somewhere else. And all that means is that the whole system conspires to act as though the electrons are moving like a positive charge would. And that's called p-conductivity, or positive conductivity. And so now the game then is we've got the transparency. We have to find the right materials to put inside the semiconductor to make the p kind and to make the n kind. And once you've got those, then you've got all of the ingredients that you need to make the electronics that makes our lives so nice. Okay? So that's conductivity. So this band gap that I've just described and on the conductivity that we've just talked about, this is the basis to explain all kinds of different things. You can make transistors now, and that's logic. That's all the stuff that moves around in your computers. You can make circuits, and you can make them transparent if you want to, too. Solar cells, not just the electronics, not the metals on the outside that I mentioned before, but the stuff that does the absorbing of the light. These solar cells are transparent to light of low energies, but they absorb the visible light and they separate the charge. You need a semiconductor to do that. In fact, it's a really good thing that a lot of the work that we do in transparent electronics is pertinent to other kinds of band gaps too, because when you try to make semiconductors that are transparent, you make a lot of semiconductors that are not transparent. And you've got to use them for something. And in fact, one of the successes of the work that we did was material that Doug invented, which was a very, very absorbent material that can be very, very thin and absorb the light very easily indeed, and be useful in a solar cell if some of the students get it to work. The other way you can find them is in a light-emitting diode, which is really a solar cell that runs backwards. This time now you take the transparent conductors, you push electrons in, and the electrons and the p-type current join together and emit light, and then it leaves the material if it is transparent. And light-emitting diodes revolutionize our lighting now. We've got diode lighting all over the place. You can take it further and make lasers out of them too. And there's another thing that you can do, which is to convert heat into current to do useful work. And here's Matt Damon doing just that in the movie The Martian. Thermoelectric generators are semiconductors where you combine the P and the N in exactly the right way to convert waste heat into useful work. And so that's something that you can do. It's a good movie, by the way. They do the science well. Okay, so how do we make them, and what form do we make them in? In my lab, we make thin films of semiconductors because that's the way that you use them in these devices, and most of the time what we're interested is in thin film material. So we better set the stage for thin films, and let's start with something thin, which is the typically example is a human hair, which is about 100 microns. Now this box over here, this big box, is 10 times deeper than this thin box at the top. So that gives you a scale of 10 to 1. So if this human hair, this is an electron micrograph of a human hair, were to fill this box, then a red blood cell, which is this thing over here, would fit into the top box over here. See a scale? If you were to go 10 times smaller, you'd get to 1 micron, which is a wavelength of an infrared light. And if you were to go 10 times smaller than that, you'd get to 100 nanometers, which is about the size of a virus. And 10 times smaller than that, you'd get to 10 nanometers, which is about a cell membrane. And smaller than that, you would get to atomic scale sizes. So typically the films we make in my lab are about 10 nanometers to 100 nanometers thick. So we're somewhere in here. Very, very thin films. So here's a picture of my lab. There are many ways to make thin films, and at OSU we have wonderful facilities to make films in all kinds of different ways. And the one that I use is called pulsed laser deposition. And to make a film in this way, you need a big laser. That's this orange thing over here. It's got lots of energy in it. And you need a vacuum chamber. That's that shiny stainless steel thing over there. And you pump all the air out of it and make sure that there's not enough, no hydrogen and stuff to bounce into the atoms. And you need some hardworking students. And once you've got that, you take a target of the material, you make whatever material it is you're interested in, you press it into a target, put it into this vacuum chamber here, turn on the laser, pump it into the target, and you see this beautiful plume here like this, and the material spews off like this, and you catch it on a glass slide that's sitting up over here. And when you pull it out, it looks like a glass slide, which is just as well because we wanted something that was transparent. You can't see through it. But there really is a film there, and this one here, you can see it glowing red. We shone UV light on it, and it glows red, which means that we had put some materials in here, some dopants in here that make it glow red. And so this is actually another application that this material might have. So how do you decide what material you're going to evaporate? Well, the thing that I do is to call up a friendly chemist and say, Doug, what shall I make? And he'll say something like, why don't you try barium copper sulfide fluoride, for example, because copper sulfide is already a pretty good p-type conductor, but it's not transparent at all. And if you were to stick some barium fluoride between the copper sulfide layers, I bet you the band gap would increase. That's a good idea, Doug. Let's try that. And maybe we can put some potassium or something in there to provide the extra electrons or the extra p-type stuff. Yeah, we'll try that, and let's see if it works. So what we want to do is to measure the band gap, and we measure the transparency to see if the material works as advertised. And indeed, it does. So this graph shows you the wavelength over here on the bottom scale here, going from ultraviolet over here, that's 200 nanometers, to infrared over here, and this is the visible region over here. Now focus on the green curve. That tells you how much of the light goes through. This light here is going through. It's almost 90% of it is going through, so it's transparent to all of these wavelengths over here, and then it starts to fall off. And this dramatic fall off over here is the band gap, which in this case is about 350, 370 nanometers. It's a transparent material, as you saw in the slide before. Now, the green is not actually the data we measure. What we really measure for transmission is this light, this blue curve over here, which has the bumps in it. And in fact, some of the light is reflected as well, because you always reflect from everything, even a piece of glass. If you can see your reflection in a piece of glass, you always lose a little bit. And it also has bumps in it. And the bumps are nothing other than what you're used to seeing on the road on a rainy day when there's been oil on the road. These are oil slicks, and they are a result of light interfering when it reflects at the two interfaces of the thin film. And when the film thickness is exactly right, then you get extra color reflected this way, and the other colors go through. So this is understood. We understand that. We can actually do clever things with that too, but here we have the transparency that we wanted. We can also control the band gap. This change in the absorption here is something that can be moved from one wavelength to another, and that's really important when you're making devices as well. It's important to be able to pick exactly which band gap you want. And then we measure the conductivity to see how much the conductivity can change. And this is a logarithmic scale. It shows that we can change the conductivity by a factor of, let's see, 1, 2, 3, 4, 5 orders of magnitude. Each of these is an increase in conductivity by a factor of 10, just by changing the amount of potassium in this case, just by a little bit, from up to a few percent. And so we've changed it 5 orders of magnitude this way. For the experts amongst you, this is a temperature scale over here, and you can see that in the process, we've changed the material from being a semiconductor to actually being a metal. And that's also useful, because imagine if you could make a device in which the semiconducting bit was one material, and just by changing what stuff you put into it, you could make it a metal on the outside. You wouldn't have to change the material at all. So that's really useful to be able to do that. Now, once you've got it, you'd like to be able to make sure that you actually made the thing correctly. So you have to take a look on a scale. And here's a bar of about 200 nanometers. Here's one of the films we made. This was barium copper tellurium fluoride in this case. And you can see that this kind of looks like a glacier. That's because we broke it. And we looked at it with a scanning electron microscope. And we have really very good equipment here at OSU to look at things on this scale. Sitting here on a substrate, this is air above it, and the film surface is very, very smooth, which is good, because you want to make devices out of it, and you don't want those electrons to go off in some random direction. You want them to go straight through like this. But on this scale, 200 nanometers, there may be a couple of thousand atoms in there. You can't actually see the atoms. And you really do want to see the atoms, don't you? You do. Well, there they are. This is a transmission electron microscope, which allows you to see things on the 10 nanometer scale. And I counted these atoms myself. I've never seen atoms before. It's really beautiful when you can look at them. There are about 50 of them right here. Those are actual atoms. In this case, the transparent conductor is zinc sulfide, a different one that we were working with. And you can see this lovely interface over here. And we're actually able to count the atoms and make sure that they are exactly where we wanted them to be. I think that's remarkable. Now let me say one more thing about materials research. It's not only a game of trial and error and thinking up things, okay, maybe I'll try this today, maybe I'll try that tomorrow. Maybe what we could do is to use the very computers that we make out of this stuff to help us design new materials. And we can do that. Well, not me, you need a theorist to do that. My colleague Henry Jansen and Günther Schneider over there are the people who can actually do these calculations. But what you do is you decide what atoms you want, and you decide what position you want to put them in. Right? That's the structure of the material. And then you feed that to the computer. And if you've written the programs correctly, and we can do this, the computer can tell you, it gives you a picture like this, and this stuff, these lines over here that look like spaghetti, we actually call it a spaghetti diagram. They can tell us exactly what the properties are. They can tell you the band gap, they can tell you the conductivity, and so on, and then you can make the device. Now this is quite a problem for a computer, and you need lots and lots of computing power to be able to do this forward problem this way. And you need to be, we make approximations as well. So what works well for one kind of material doesn't work as well for another kind of material. So it's almost like an experimental project in itself to do this kind of calculation. But we're getting better at it, and people are getting better at it all the time. But wouldn't it be fun if you could turn the whole thing around and decide what properties you want, and then ask the computer to tell you where to put them and what atoms to use? Now that would be fun. And this is a much, much harder problem for us to solve, and we need really smart theorists to be able to do this. And I think eventually, one of these days, we'll be able to do it, maybe. And we can ask the computer, and you can say, hello, computer, I want to make whatever it is. So, okay. So I want to change gears a little bit. Even if we had that computer would be hard-pressed to tell us about what to do, how to make a superconductor. Now, how many of you own a superconductor? Not so many, one or two. Yeah, I thought so. In fact, they are around, and you do know about them. You use them, and they're part of us. But not so much, because superconductivity is a very exotic state of matter. It's cool, pun intended, very bad pun, but you know. And the reason that it is not so common is that it's quite exotic, right? So normal electrons, the kinds that we've been talking about up until now, they are negatively charged and they repel each other, right? Just like the electrons in this person's hair here, right? So she's been put her hands on a Van de Graaff generator, and her hair stands up on end because these electrons are trying to get away from one another. But in a superconductor, the electrons conspire with their host lattice that they live in to actually attract one another. So this negative electron comes along, and the positive ions contract a little bit, and the second electron comes along, and it sees this increased positive charge, and it goes along too. So it's kind of like, imagine you had, I don't know, 2 dogs or something. Suppose you had 2 dogs that hated each other. They would not be in the same place at the same time, but they liked bones. So dog number 1 comes and it drops a bone, and dog number 2 comes along and picks up the bone, and then goes and drops the bone over there, and the dog goes like this. And they follow each other around. And if you didn't know about the bone, you would see 2 dogs that moved like this, and they would be in a pair, and they would be, but if the bones weren't there, then the dogs would not be apart. So anyway, electrons are kind of like these dogs, and they, oops, we're going in the wrong direction here. There we go. So this attractive interaction with the lattice is what you need to make superconductivity, but it's very, very delicate, and you need a low temperature to do it. So here's a picture of a superconductor's resistance or inverse conductance. So this is how badly it conducts. So this is a highly resistive material, doesn't conduct very well, and as the temperature goes down, all of a sudden the resistance disappears completely, and it's completely zero over here. This is infinitely conducting material. So these are these pairs that I was talking about. They can flow through a material, and they get around any imperfection. They don't care about that at all. Infinitely conductive. That's a wonderful thing. Now, just to get a scale of the temperatures, let's take a look here. This is the Kelvin scale, and on this scale, this material here, yttrium barium copper oxide, is superconductive at about 90 Kelvin. Now, on the Kelvin scale, we are sitting here at room temperature, which is about a little bit off the scale over here. Ice temperature is 273 Kelvin. That's 0 degrees. That's about here. The coldest temperature that has ever been recorded on the surface of the Earth was 184 Kelvin, or minus 90 degrees C, about, in Vostok, which is a Russian base in Antarctica. So it was a cold day in hell, you might say. And liquid nitrogen becomes liquid at 77 Kelvin down here. And this is actually the discovery of superconductivity at 90 Kelvin was technologically and scientifically a very important thing. Technologically, because it is a superconductor above liquid nitrogen temperature. So you can take liquid nitrogen, which is some stuff over there, and you can make it relatively cheaply. My advisor, Blas Cabrera, always used to tell me that liquid nitrogen is the price of milk. Whereas most materials are superconducting at liquid helium, which is the price of whiskey. It's different. Now, scientifically, this is very interesting, too. I'm not going to go into that part of it here, but suffice it to say that this material, yttrium barium copper oxide, superconducts at about 90 Kelvin. And this was a very important discovery. This is what happened when I first went to Munich, and this is what I started studying at that time. Now, what can we do with a material that doesn't have any resistance at all? Well, if you are an electron and you're going along in a normal wire, so in something in this region over here, in the normal region, you lose a lot of the energy because you're bumping into imperfections in the lattice, and it's very inefficient for energy transmission. It's great if you want to make toast because it makes stuff hot, or heat your house. That's good. You want that kind of thing. But if you want to get energy over large distances, you really do need a superconductor. You need something that has zero resistance. So that's what we look for. Now, just to get a scale of all of the other superconductors around, here's a history lesson for you. The x-axis starts at 1900. In 1911, superconductivity was discovered in mercury at about 4 Kelvin. So this is below the level of liquid helium. And in the ensuing 100 years, we found many, many materials that superconduct at low temperatures. And these are the ones that are really used commercially now. But we need liquid helium, which superconducts at 4 Kelvin. It's a very low temperature. It's very expensive to liquefy it. And helium, we just don't have very much of it in the atmosphere. Nitrogen, it's great. It's all around us. We can liquefy that very easily indeed. Now, all of these materials here superconduct below 50 Kelvin. And so even if you went to the surface of Pluto, they wouldn't be superconductors. You really do need something very expensive like liquid helium to make them superconducting, to conduct electricity with no resistance at all. So it was very exciting when yttrium barium copper oxide was discovered in 1986 or 7 that we could make superconductors above liquid nitrogen. So they would be superconductors on the surface of Pluto. And if you were on Pluto, they might even qualify as room temperature superconductors if you put your room on Pluto. But they wouldn't be room temperature superconductors here in Corvallis, and not even in Vostok, where it gets pretty cold. But recently there was an interesting report in Nature just a couple of months ago of superconductivity at 203 Kelvin, which would be room temperature in Vostok. So you could get these properties of electrical conductivity, infinite electrical conductivity in a room in Vostok, but not here. Now, it was room temperature but it wasn't exactly room pressure. This was 150 gigapascals, which is 1.5 million bars. So we're not quite there yet, so don't start looking for this on your shelf anytime soon. And it was a hydride of sulfur, which, aside from anything else, is kind of smelly. But okay. So it's not all pie in the sky. This yttrium barium copper oxide, though, this is actually a kilometer of experimental cable that was unfurled in Essen in Germany and was actually used for power transmission in the city itself, so short distances are possible. And this kind of cable actually has to carry the liquid nitrogen with it in order to keep the superconductor cold. So you can see if it did work at room temperature, we would be able to transmit our power from here to, from the Columbia River all the way to Los Angeles. Isn't that a good idea? Without any dissipation at all. It would be enormously useful for efficient energy transmission. The other place where you've encountered superconductors surely is an MRI. Here is a magnetic resonance imaging machine. This has a big superconducting magnet in here, and we need these big magnets to make, image people here. You need to be able to flip the proton spins around in your body, make these hydrogen atoms do exactly what you want, so you can image what's going on in your body. Here's a beautiful image of the brain that comes from one of the brain research projects, showing you all of the connections in the brain. This was imaged with MRI and these large magnets, and you need superconductors to make the magnets, to make the fields large enough to do that. But once you've set this enormous current in motion inside a superconductor, it just sits there for as long as you care to watch it. And that's actually wonderful for energy storage too. So if you make these really big magnets with lots and lots of current in them, you just go away and leave them, and they sit there forever without losing any energy at all. So that's great. But you do have to keep them cold. And as soon as it becomes warm again, then you have this resistive property, and you no longer have a superconductor. The other place that we use superconductors a lot is this device is called a Squid. Squid stands for Superconducting Quantum Interference Device. And what it is a very, very, very sensitive magnetometer. It can measure the tiniest, tiniest changes in magnetic fields. Here's the scale. This is about the size of a dime. And the squid itself, it's not one of these kinds of squids. Those live in the ocean. One of these is really very tiny and sits in about a 1 micron space inside here and measures these really tiny magnetic fields. And so geologists use them. They actually take them out into the field with liquid nitrogen, and they go looking for ores. They look for all kinds of stuff with them. We also have the ability with these exquisitely sensitive magnetometers to directly measure the transmission of an electron inside a neuron, for example. Not like MRI, but actually the motion of an electron like this as it goes along a nerve cell, say, in your brain. And the squid can detect the motion of that electron from outside your head. They're that sensitive. And so you can see here's somebody thinking about something here, and there's the pattern. And it's also much faster than MRI, which is really helpful if you would like to image the brain of a squiggly little bit of protoplasm like a baby. The other thing that's also really interesting about them is that superconductors, being this exotic state of matter, are really good candidates for a quantum computer, which is a kind of computer that would be able to do calculations that we can't do with regular computers now. And these superconductors might be such a thing that would one day be part of a quantum computer. The last application that I want to tell you about is magnetic levitation. And this is not a real superconductor. This is, though it is a magnetically levitated train. This lives in Japan. And these are two magnets floating along one another. And the train is basically floating on a track. And this means that the train can go with very little friction in the bearings, and that's something that is really desirable. But superconductors have a property that is related to this that makes them really interesting. It's similar to infinite conductivity, but it's not quite the same. Once the superconductor goes through its transition temperature, what it does is expel the magnetic field from inside the superconductor completely, and basically makes it into a perfect magnet. So you go through the transition temperature, and all of a sudden the material just throws out all the magnetic field lines. It looks like this. Here, this thing is a superconductor, and these blue lines here represent magnetic flux. It throws them out like this, and it makes it into a magnet. So now the superconductor is able to float a magnet on top of it, or it will float on top of a magnet. And if you could make these and put them inside the train, then, or anything, you could levitate things and have frictionless bearings and so on and so forth. Now, some superconductors, like yttrium, barium, copper oxide, have a slightly different property than that. They do try to throw the magnetic field out, but they actually keep some of the magnetic field inside in these kind of tendril things in what we call flux tubes or flux vortices. And they stick inside the material, and they trap the magnetic field in exactly the right way that can be useful to us. So the rule of quantum mechanics, and remember we all obey quantum mechanics, right? The rule in quantum mechanics is that once you have a certain amount of flux in a superconductor, it doesn't change. And so you can use this property to levitate things. So the last thing I'll do is leave you with a demonstration of this. I'll get my trusty assistants here to do this. Superconductors. Don't tell the safety people. Okay. So inside the liquid nitrogen bucket over here, you can see, is a thin film of yttrium, barium, copper oxide, which we can put on a superconductor. Whoops. Tell me when I have it right. You see it? Okay, so there it is floating on a magnet, pretty stable. And let's try this little one, it might work better. Okay, stay. There we go. So it can even hang, but it's pretty stable. If we put it on this one here, this is a circular magnet now. And it can spin. Do that. And I think it can spin upside down. Yeah. Ooh, there you go. I planted them in the audience. Okay. Let's just leave it over there. And let's see if we can make it be a train. Just leave it there. Well, if you'd like to come up and play with these things afterwards, then you're more than welcome to do that. So superconductors and semiconductors have been the thing that I've worked on a lot. And in fact, they might seem like they're very different. But in fact, for me, they're a similar kind of materials problem. I started working on semiconductors because superconductors had a particular impurity in them that was kind of in the way. And that was the thing that turned out to be a transparent conductor. So it was working on one thing that actually led to the other, like this. So there are lots and lots of different kinds of problems to solve in materials. And you just wander from one to the other, and it's all exciting, and you'll find something. And if it's scientifically interesting, we'll find a use for it. Thanks very much.
So that's a wonderful talk. She's willing to take some questions, and if you're going to ask a question, please come to the microphone here, or Debbie or somebody will pass the microphone to you. Questions?
Did you ever try the buckyballs?
I have never made buckyballs, no. And lots of people have. Anybody here made buckyballs? They are superconductors, though. You can make them into superconductors. And close to buckyballs are carbon nanotubes and graphene, which Ethan Minot in our department studies. So.
Yeah, when you do your laser deposition, you're depositing the bulk materials mixed in the stoichiometric ratios. You're not doing layer by layer construction.
You can do both. So when we take a target, it's usually made stoichiometric, exactly the ratio we wanted. And pulsed laser deposition is interesting in that it usually preserves that ratio when you do the deposition. Other deposition methods don't do that. But you can also do layered targets. You can go from one and then move another target in place and do the other, and another target in place and do the other. I'm looking at Bethany here. That's what she does at the moment right now.
But you basically rely on self-assembly, right?
Yes, you rely on self-assembly, but there are some groups that actually will do it layer by layer and try to make it almost like molecular beam epitaxy. You can do it from single layers, but not usually that way in my lab.
So you said that that was a thin film superconductor?
This one here.
How thin is thin?
How thin is thin? Are you talking about this one here?
Yeah.
Yeah, so the question is that the thin film in here, how thin is thin? I don't know. I didn't ask you. I wouldn't tell me. But I imagine it's about, I would imagine it's about 100 nanometers or at most 1,000 nanometers thick. And possibly the one that he guaranteed for longer is a little bit thicker. I don't know. Manuela.
If I understood, that's frictionless, but why did it slow down?
This one here?
Wait,
Oh, this one over here. It's probably because, I'm not sure actually. Air resistance? Ooh, I don't know. I don't think air would be that resistive. It may have to do, I think it's more likely got to do with the fact that the magnetic field profile is not exactly as uniform as you would like it to be to keep it going and keep the flux exactly the same. It didn't like that question at all. Let's try this one. Oh, that's interesting. Let's see how that one does. It doesn't want to do it either. Maybe we can put them together and see if that works. Try that later. More questions.
Could that be because the temperature? If you put this whole thing in a liquid nitrogen environment, it keeps the temperature to be -77 homogeneously, then maybe it will not have this friction because it's in the room temperature.
So
things change, so you can't keep it -77.
There's some porous stuff over here. It's actually got liquid nitrogen floating with it right now.
Okay.
Yeah, so it is in there.
Yeah.
When you have transparent properties, can you also make them refractive? That is.
Refract? You mean to refract light? Or
Yes, rather than just transparent, the certain wavelengths can also give them refractive properties.
they will reflect. They will have a certain refractive index, and they will refract as well and reflect just normally. Yes.
Yeah.
To what do you attribute your drive to innovate?
To what do I attribute my drive to innovate? I like figuring out how things work, and
why is that?
I really don't know. Let me think about that. David, can you answer that? I think it's, I like the pattern, the way that things fit together. And I've always liked to solve puzzles. And I achieve great satisfaction from putting in the last letter in the crossword puzzle, the last piece of the jigsaw puzzle. And I suppose that transfers over to finding out just exactly how something works. When it fits together, you think, yeah, must be right.
Okay.
Okay.
Let's thank Janet again for a wonderful talk.